Particle physics is the study of these tiny building blocks and the forces that bind them. It seeks to answer profound questions about the nature of matter, energy, and the universe itself. At the heart of particle physics lies a theory called the Standard Model, like a periodic table for particles. It's a remarkable achievement, but it's not without its puzzles. Enter supersymmetry, a theoretical framework that proposes every particle we know has a superpartner. This idea could offer solutions to some of the most pressing mysteries in the field. So, what exactly is this supersymmetry and how does it fit into the grand scheme of particle physics? Let's delve into that. Supersymmetry, often abbreviated as SUSY, is a principle that proposes a relationship between two basic classes of elementary particles. Now, you might be wondering how this principle works. Well, let's break it down. In the world of particle physics, two kinds of elementary particles exist: bosons and fermions. Bosons are force-carrying particles. They govern the fundamental forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces. Fermions, on the other hand, are the building blocks of matter. Electrons, protons, and neutrons, for instance, are fermions. Supersymmetry comes into play by proposing a fascinating idea. It suggests that for every boson, there is a corresponding fermion, and vice versa. These corresponding particles are known as superpartners. So, in a supersymmetric universe, an electron would have a superpartner called a selectron, a boson, and a photon would have a superpartner called a photino, a fermion. This notion proposes a beautiful symmetry between particles and forces. It's like looking at a perfectly balanced equation where every element has a counterpart on the other side. This symmetry is not just aesthetically pleasing, it also offers compelling solutions to some of the most perplexing questions in particle physics. However, there's one small hitch. Despite the elegance of this theory, our current experiments and observations don't seem to align perfectly with it. The superpartners that supersymmetry predicts? We haven't found them. Not yet, at least. But why is supersymmetry so significant in the realm of particle physics? That's what we're about to explore. Supersymmetry holds a significant place in particle physics for a number of reasons. Firstly, it provides an elegant solution to one of the most perplexing problems in physics, the hierarchy problem. This problem arises from a discrepancy between the observed weakness of gravity compared to other fundamental forces and the predicted strength of gravity according to the Standard Model of physics. Supersymmetry, with its introduction of superpartners for known particles, allows for a delicate balancing act. This balance cancels out the extreme quantum fluctuations that would otherwise result in an incredibly strong force of gravity, thus resolving the hierarchy problem. Secondly, supersymmetry could potentially provide us with a candidate for dark matter. Dark matter, as some of you may know, is a mysterious substance that makes up about 25% of the universe yet remains undetected. The lightest supersymmetric particle, often referred to as the neutralino, is a perfect candidate for dark matter. It's stable, neutral, and interacts weakly with other particles, characteristics that align perfectly with our current understanding of dark matter. In addition, supersymmetry also promises to unify all fundamental forces of nature at high energies. This idea, known as grand unified theories or GUTS, suggests that at extremely high energies, the electromagnetic, weak and strong nuclear forces all become one and the same. Supersymmetry, with its additional particles and symmetries, provides the mathematical framework to support this unification. Lastly, supersymmetry also has implications for string theory, a theoretical framework where the point-like particles of particle physics are replaced by one-dimensional strings. Supersymmetry is a necessary condition for many formulations of string theory, giving it additional importance in the realm of theoretical physics. However, despite its potential, supersymmetry remains a theory. Why so? Let's find out. While supersymmetry offers intriguing solutions, concrete evidence to support it has been elusive. Two of the world's most powerful particle accelerators, the Large Hadron Collider and the Tevatron, have been at the forefront of this search. These colossal machines, capable of smashing particles together at near light speed, were expected to provide the first glimpses of superpartners, the new particles predicted by supersymmetry. But so far, these elusive entities remain unseen. The absence of direct evidence at these high-energy frontiers has sparked intense debates within the scientific community. Some researchers argue that we may simply not be looking in the right way or at the right energy scales. Others suggest that the superpartners might be hiding just out of reach of our current technology, waiting for the next generation of particle accelerators to reveal them. Yet there are also those who propose a more unsettling possibility. What if supersymmetry, elegant and compelling as it is, turns out to be wrong? Could it be that we've been chasing a shadow, a beautiful mathematical ghost that doesn't exist in the physical world? The implications of this are profound, for it would mean that the standard model of physics, despite its many successes, is fundamentally incomplete. It would leave us with a universe filled with unanswered questions, from the nature of dark matter to the origins of the Big Bang. So where does this leave us in our understanding of particle physics and the role of supersymmetry? We stand at a crossroads, peering into the unknown, waiting for the next clue to emerge from the quantum depths. And though the path may be fraught with uncertainty, one thing remains clear: the quest for understanding, the drive to uncover the fundamental truths of our universe, will always push us forward. Because in the end, the journey is just as important as the destination. The mysteries of particle physics and the role of supersymmetry remain a fascinating field of exploration. Indeed, the journey into the heart of matter, into the very building blocks of the universe, continues to be an exhilarating adventure. Our current understanding, as encapsulated in the standard model of physics, is far from being the ultimate answer. It leaves us with puzzles and paradoxes, and it's here that supersymmetry comes into play. Supersymmetry, or SUSY for short, proposes that every particle we know has a much heavier superpartner. This theory, if confirmed, could be a game-changer. It could provide answers to some of the most perplexing questions in physics, such as the nature of dark matter, or why the universe is composed of matter and not antimatter. But despite its promise, evidence for supersymmetry remains elusive. The Large Hadron Collider, the world's most powerful particle accelerator, has yet to detect these hypothetical superpartners. This lack of evidence has led some to question the validity of supersymmetry, while others remain hopeful that future experiments or more powerful accelerators might finally uncover these elusive particles. The implications of this ongoing research are profound. If supersymmetry is confirmed, it could revolutionize our understanding of the universe, opening up new avenues of research and perhaps even new technologies. On the other hand, if supersymmetry is ultimately disproven, it would force us to reassess our theories and embark on a new quest for a more comprehensive model of particle physics. But regardless of the outcome, one thing is clear: the journey is far from over. There are still many questions to answer, many mysteries to unravel. We are just scratching the surface of the vast cosmic puzzle that is our universe. As we continue to probe the mysteries of the universe, who knows what fascinating discoveries await us?